We're going to switch gears here and talk about electrolytes, but we'll bring it back to acids and bases shortly. And an electrolyte is basically a substance that when you add it to water, conducts electricity. So added to water, so added to H2O, it forms a solution that conducts electricity. These are normally soluble ionic compounds. So when we looked at our solubility rules weeks ago, all those ionic compounds that dissolve in water, so things like sodium chloride or sodium hydroxide or hydrochloric acid or potassium nitrate, these are all very strong electrolytes. And what's going on here, if we dissolve these in water and we try and pass electricity through it, we see something kind of interesting here. So I'm going to draw an electrode and I'm going to hook it up to a battery, maybe a 9-volt battery or maybe a car battery, who knows what. And the electrodes can be sort of carbon or platinum wires or something. And when you add an electrolyte to water, okay, it is going to conduct electricity, and the reason is that electrolyte, which is an ionic compound, actually breaks down into ions in solution. And so it breaks down into positive ions that are cations and also negative ions that are anions. And it's these anions and cations that can actually move through the solution and conduct electricity. So if we think about the flow of electricity as the flow of positive charge, and so we've got our positive charge moving into one electrode and presumably coming back to the negative side of the battery like that, how does it cross the gap, so to speak, in between? And the way it crosses the gap is, remember, electricity is just simply movement of charge. And so the positive charge that is coming down to the left-hand electrode has to go somewhere, and what actually happens is that the cations move from left to right, so that positive charge flows in that clockwise direction here, and the negative ions, they actually flow as well, and the flow of negative ions is exactly in the opposite direction to the flow of positive ions, and so they flow in the opposite direction here and complete the circuit. So the positive ions flow this way, the negative ions flow the other way. Whichever way you look at it, electricity is passing through the solution. If you hook it up to a light bulb, then the light bulb will brightly shine as the electrodes are dipped into this solution here. So essentially those ions in solution are what's causing it to conduct electricity super well. We have some terminology here. Our electrolytes we actually classify as 3 different kinds. We have what we call strong electrolytes. And strong electrolytes conduct electricity super well. We also have weak electrolytes, and weak electrolytes, they don't conduct nearly as well. So if you hooked up a light bulb to this, the light bulb would be very, very dim. So they conduct electricity poorly. And the third kind is actually non-electrolytes. And so non-electrolytes, if I could squeeze them down in the lower left corner here, these are things that dissolve in water and do not conduct at all. So they do not conduct. And we might want to go ahead and ask ourselves what's going on here. So why is it that some electrolytes conduct very well and some conduct very poorly and some don't conduct at all, which means that they're not electrolytes, they're non-electrolytes. And the answer is that a strong electrolyte completely breaks down into ions. So it undergoes what we call 100% ionization. So that means for every 100 of these ionic compounds we throw in the water, they completely break down. And if you've got a weak electrolyte, they actually only partially ionize. So I'm going to say less than 100% ionization. But in reality, you know, it might only be 1 or 2 or 3%, let's say. And if you've got a non-electrolyte, essentially what is happening here is that you get 0% ionization. So although you might add something to water and it may dissolve, it does not break down in any shape or form, and doesn't make any ions at all. So strong electrolytes are typically ionic compounds that dissolve extremely well, completely break down and give ions. Non-electrolytes do not break down at all, there's no ions formed, and some substances are sort of in between. Maybe only 5% of them actually break down and form ions, and so it's only those 5% of those compounds that are broken down, and only 5% of the ions are in solution, so it only conducts about 5% of that electricity. Now you might be saying, well, that's very exciting about electrolytes, but what do electrolytes have to do with acids? And it turns out they have a lot to do with acids, because we have acids that we call strong, and strong acids are things like hydrochloric acid or HCl. And the reason it's a strong acid is that it completely breaks down 100% of the time in solution. So that HCl completely breaks down. 100% of those HCl molecules break down, and for every 100 molecules you've got 100 H plus ions and 100 of those counter ions of those chloride ions. And it's the H plus ion that makes something an acid. So hydrochloric acid is a strong acid, and it has hydrogen in it, but the reason it's strong is that every hydrogen breaks off when it hits water. Now you compare that to my favorite acid, which is acetic acid. And acetic acid is a weak acid. When you have vinegar, you don't have to worry about your teeth completely dissolving, whereas if you obviously gargle toilet bowl cleaner, it's going to do very nasty things to your teeth very, very quickly. And what's going on here is that the acetic acid, which is a hydrogen ion attached to acetate, doesn't completely break down. And so we can write an equilibrium, and the equilibrium is going to look something like this. So there's my acetic acid. I'm going to draw an equilibrium arrow. And notice I'm going to draw this arrow so it's short in the forwards direction and it's long in the back direction. And that means that it doesn't go forward very much at all. It mainly stays on the left side. So I've got sort of a shift to the left here, if you like, or in the sense that the left-hand side is much more important. So there's my hydrogen ion, and there's the acetate ion, one of those 11 polyatomic ions we looked at back in, oh gosh, what was it, February now? And so we can say for every 100 of these molecules, 95, let's say, don't break down at all, and only 5 out of the 100, so 5% break down. So even though you might have 1 mole of hydrochloric acid and 1 mole of acetic acid, it turns out that 1 mole of acetic acid will only form 0.05 moles of hydrogen ion, let's say, as opposed to something like hydrochloric acid, where that 1 mole would make 1 mole of hydrogen ion. And if it's the hydrogen ion that makes things acidic, obviously if you don't have very much of it, it's not going to be a very strong acid. So it's not going to have a large imbalance of H plus compared to everything else. So we call it a weak acid because it only partially breaks down, and that's also known as a weak electrolyte. So we've talked about acids being either strong or weak, and if they're strong, they completely break down, and if they're weak, they're only partially breaking down. And so given that it's the H plus ion that makes an acid, if it completely breaks down, it makes tons of this stuff, right? And if it partially breaks down, it makes just a wimpy amount of H plus. We also classify acids as to the number of H plus ions they have per molecule. And so for instance, if you've got a monoprotic acid, so a monoprotic acid, so mono, you might recognize that prefix meaning one. Protic refers to H plus, and it turns out the hydrogen atom has a proton plus an electron, but when it forms a hydrogen ion, it loses the electron, and so it really is just a H plus, it's just a proton at that point. And so a monoprotic acid is one that has 1 proton per molecule, so HCl has only got 1 hydrogen total, so of course it has to be monoprotic, but acetic acid, my favorite acid, is also classified as monoprotic because although it's a weak acid, in theory it can break down and make up to 1 hydrogen per molecule. Of course, it's got 4 hydrogens, it's got 1 there and it's got 3 there, that's 4. But remember, the hydrogens up front or at the very end are the acidic ones. The ones in the middle are almost never considered acidic. We also have something like maybe HNO3. HNO3 is nitric acid, and again it's a strong acid because it completely breaks down and makes 1 H plus the nitrate ion. We also have acids that can make 2 or 3 or 4, and so we have names for those. Diprotic acids are ones that have 2 H pluses per molecule. And the classic example of a diprotic acid is H2SO4, which is sulfuric acid. And sulfuric acid is one of those substances that the amount of sulfuric acid a society makes is supposedly related to how advanced that sulfuric acid is, no, that society is. And the reason it's diprotic is that both those hydrogens can come off when it dissolves in solution, and it can form two hydrogen ions and a sulfate ion. We also have a common example of a triprotic acid, and if you like Coca-Cola or Pepsi-Cola, then you're drinking a triprotic acid, and again, it's got 3 hydrogen ions per molecule. Phosphoric acid is H3PO4, and it can form up to, it normally doesn't give all 3 actually at one time, but we can say it can give up to 3, and so 3 H pluses, and if you recognize your polyatomic ions, that is your phosphate ion right there. So that is phosphoric acid. Not terribly strong, it's quite a weak acid. It doesn't completely break down, so it only breaks down a few percent, as opposed to 100% of things like hydrochloric acid, but it can give up to 3 hydrogen ions per molecule, hence it's triprotic. Sometimes we actually go ahead and we say, gosh, that's kind of complicated, and is there any simpler way to talk about this stuff? And we often talk about polyprotic acids, and poly means many, so polyprotic means the acid has got many protons. And what do you mean by many? Well, it just means it's got more than one. So diprotic and triprotic and tetraprotic and whatever comes after that would all be classified as polyprotic acids.